Hello everyone, myself P. Ramakrishna, Associate Professor from Anurag University. Today I am going to explain the process of simulation, synthesis, and implementation of a design on FPGA using Xilinx Vivado IDE platform. So, before going to start the process of this implementation, let me discuss a brief about FPGA design flow. See, so the FPGAs is used to make a logic level circuit diagram to a product. The main objectives of this process is create a Vivado sourcing HDL model targeting a specific FPGA device located on the Z board. And the next step, create a Xilinx design constraints file to constrain some of the pin locations on the FPGA. Simulate the design using the Axiom simulator provided by the Xilinx. Then after synthesize and implement thus design to the FPGA and generate the bit stream, configure the FPGA using generated bit stream and verify the functionalities. These are the objectives of today's practice. Here we can see the FPGA design flow or black diagram. So very first step of any design is to define the specifications of the given design. So then, according to that specifications, we have to create a code like Verilog HDL or VHDL. After creating that code or writing a Verilog HDL code for the given design, so we need to elaborate the design to get RTL. The RTL is a register transfer level. So here we can get the gate level schematic of this design. So it may be the digital design. The next step of after getting the RTL schematic, we're going to synthesize and create a netlist. For synthesis is the process to create a netlist and analyze the hierarchy of our design. So to verify the functionality of the design, we need to simulate it. Then we can get the simulated waveforms according to the given specifications. So that's what the next step of after the synthesis. So after completion of this functional simulation and synthesis, we are going to implement the design. So to implement the design, we should follow the further three steps. The first one is translate the design and mapping that, and then after placement out. So while going to translate here, it measures all of the input nets and design constraints and outputs a Xilinx native generic database file that is called NGD file. After completion of this translation step, we can get that NGD file. So immediate after this translation, go to that mapping. Here it maps the logic defined by an NGD file into an FPGA elements such as CLVs and IOVs, configurable logic blocks and input-output blocks. The output design of this map is native circuit description file, that is called NCD. After completion of this mapping, we are going to put the next step, place and route. Here it takes the mapped NCD file, places and routes the design and produces an NCD file that is used as input for a bit stream generation. So these three steps are done at the implementation level. After this implementation, the next step is going to simulate or timing constraints to get uh, timing to the closer of the real time. That's what timing simulation. After this completion of a timing simulation, go to the generate bit file. To generate the bit stream file, we are using generate bit file. So this bit stream file is implemented on FPGA. That is also called configuration of FPGA. So this is about FPGA design flow. So after this FPGA design, we can see that our design is converted into a product. So next, so coming to the block diagram of your jet board, it's called Jinx 7000 series. Here we can see uh, the processing system and the programmable logic PL, and the multiplex input output IOs are there. So from this diagram, we can observe that it's having a global clock of 100 megahertz on that programmable logic side, and a processing system clock for ARM processor is having a 33 megahertz and a reset pin and a RAM of a DDR3 is having a 512 megabytes for this processing system. Coming to the multiplex IO, it has a flash memory and a PMOS, a programmable modules are called to connect external peripherals. We are using these programmable modules. So here we can observe that on programmable logic side, OLED, that's what onboard OLED is available, and two LEDs like done and program. So after completion of implementation, this done LED is closed. So this programming LED is turned on while programming the device, and then it's having a HDMI port and general purpose input output pins like push button switches and slide switches. It's having 8 slide switches and 5 push button switches and 8 LEDs. That's what used for output verification. So these are the main components of this Z diagram. Coming to that user input output pins, maximum we are using those push buttons and slide switches and the LEDs. So those push buttons and slide switches are used as inputs, and LEDs are used as output. Here, the board provides 7 user general purpose IO push buttons five on that programmable logic side, and two on the processing side. So coming to the user dip switches, the deadboard has eight dip switches, switch 0 to switch 7, providing user input. So single pole double throw switches connect the I/O through a 10 kilo ohm resistor to the V adjust voltage supply or ground. So switch 0 and switch 1 and switch 2 up to switch 7 are the signal names, and we can see the number on the Z board is F22 is assigned to switch 0, and G22 is assigned to switch 1. Like this, we can use these G pins by writing a constraints file to connect the variables of your design to that FPGA. So next, the breadboard has 8 user LEDs, LD0 to LD7. The logic high from the Xilinx 7000 series causes the LED to turn on. LEDs are sourced from 3.3 volts bands. So we have a 3.3 volts band and 1.8 volts band and 2.5 volts band on that FPGA. So here we can see the signal name of this LEDs are LD0 to LD9. So the pin names on that FPGA is T22, T21 to U14. So this is the Z board evolution and development of the Xilinx 7000 series, and here we can see the structure of this Z board. So we have DDR3 and Xilinx processor and FNC called FPGA mezzanine connector. This is used to connect outside world or to interface it with different peripherals. So here we can observe that slide switches, general purpose IO, and push button switches. We have discussed in the previously 5 push button switches, 8 slide switches, and 8 LEDs. So these are the PMOS to connect the outside world or to another external peripherals. We are using PMOS. So this is the power switch and this is a power connector, and this JTAG and debug pin is used to connect the system to the board. So by using this cable, we can implement our bit file into the FPGA. So these are all called audio input output pins. So we can give input to this FPGA used as a mic, and we can take the output from this FPGA and connect to the speaker. So like this, video adapters also available. Here we have HDMI model only and a VGA model. So these two ports can be used to connect the videos to the FPGA. So this is about design flow of FPGA. And now we can go through the hands-on session. So how to design, how to simulate and synthesize the design, and how to implement on that FPGA. We'll see one by one with an example. So now I am going to discuss about this Vivado tool, how to create a project and how to simulate it and how to synthesize and implement an FPGA. So the first step of this process is just create a new project. If you have any existing projects are there, you can use this open project icon. So by clicking on this open project, we can open the existing projects here. So now I'm going to create a new project here. By clicking on this, we can create a new project. Just click on this new project. we can get a new window like create a new Vivado project here. Click on next. So here we can see the project name and the project location bars here. So here give the project name like so I'm going to design a full adder using two half adders here. So my project name is full adder using two half adders. And my project location here. This is what you can store your project in any location of your device drives. So here I'm going to store my project location here. So after this, just click on the next. So here one more window is appeared to create a new project. Project type you have to specify. Now I am going to design an RTL project. Just click on that default. It will select the RTL project. So no need to click here. Just go to that next. Window. So next step is to create a new file or already existing file you want to add. We can use add sources or add files. So that we can add existing Verilog files. Otherwise, you have to create a new file here. So here, no need to create anything or add anything files here because after completion or after creating this project, we can add a new source. So skip this step now by clicking on the next. Do you have any existing IPs intellectual properties? So you can add here some intellectual properties already available in your Vivado. So if you want to use those processors for a system design, so we can use those existing IPs. So here no need to. I am not using any IPs here. Go to the next step. So here the next step is add constraints. So if you want to add any constraint files to connect our design to the FPGA pins, so you need to create these constraints. So here no need to add any constraints here because I'm not creating any file. So after completion of this creation, so we can add the constraints like physical and timing constraints. So now click on the next button. We can get one more window. So this window shows to select the default part on this board. That's what FPGA board. Here we will be select a board by click on this boards, and so you can see the number of boards with RTX, Kintex, and Vertex like this. So now I am going to use the JET board, the Jink Evaluation Development Kit. Just click on the JET board Jink Evaluation Kit. That is what selected the parts and click on next button. So this is our new project summary of what we have created. You see, the first I have selected the RTL project name full header using two half headers, and I'm not adding any files or created any files here, any constraint files and any configurable IPs here. So I'm not adding anything here. So now I'm going to create those, and I have added a jet board here. That's what a Jinx 7000 series has. So we can see finally so we finish this project summary. After finishing that project summary, it will appear like this: project manager, and left side you can see the flow navigator here, and it has the sources window and the project summary here, what we have created, and design, how the design is running, what about the progress of the design. So we can observe in this bottom window. The left side we can see the entire process of this. So here in the sources window, we can see the design source, constraints, and simulation sources are there. We have a three folders created with design source, constraints, and simulations. Here our design file is created, and this second one, constraints. So here we have to add the Xilinx constraints to the design source, and the third one is the simulation sources. Here we need to create the simulation source like a test bench to test our design sources. Here three windows separately, three folders are created. Now I'm going to create a new source here. Just right click on that design sources, add sources. Then after we can get the add sources window. Here just select that add or create a design source. Click on that add or create a design source and click next. So here I am going to add a source file. So already I have created. Now just click on that add files, full header, click on this and finish. So we can see a full header here with two half headers. Now I'm going to add these two half headers because I'm going to design a full header using two half headers. I have created half header and added to that full header. Using these two half headers, I am creating the full header. So you can see that the full header code by double clicking on that file is highlighted because it is a full header file. It is highlighted because of it is a top module. So internal modules are half header and one half header two. So here you can see code. So you know about this Verilog HDL. So I'm not going to discuss about this Verilog HDL because time is very less. So you can see here the code. The half header, two half headers are used to create the FPGA. Now I'm going to add this half header by clicking on this add source, add create simulation, and click next. And here add files. And click OK. And you can see that the file path and the file name of this and default library it is utilized. Just finish it. Now you can see these two files are added. There is no question mark here. So now it is a design source. The design source having full headers with two half headers. So the design source is created. Now I am going to check my design whether it is working perfectly or not. Any errors are there or any problems with the design by simulating this design using Xilinx simulator. So to verify this functionality of the design, I need to create a test bench to generate the test vectors, and those test vectors will test the design So whether the design is functionally working or not. So for that, we have to create a test bench. That test bench is called a simulation source. So those test benches are created in this simulation source folder. You can observe here the simulation sources. You just right click on simulation source, add sources, create or add this simulation source. So already I have created a test bench here. Just go to that, add files. So you just select this Vivado test bench and click OK. Finish. Now it will be added here. You can see Vivado test bench. By double click on this, so you can see the test bench level A equal to 0, B equal to 0, C equal to 0. This is the first test vector generated by this test bench. And after 10 nanoseconds, it will generate this test vector. Like this, it can generate up to 4 test vectors. After writing this test bench, go through the simulation to verify the designs. Just you can observe the left side simulation there. The simulation defaults it has already. Now, just click on the run simulation. Select run behavioral simulation. See here, you can observe the waveform window. After completion of the simulation, we are getting this waveform window. So just analyze this waveform window, maximize it. Here, two inputs, three inputs are there: A, B, and C, and the output sum and carry. You can observe it by changing these input vectors. You can observe the output how it will be changed. So to see the entire waveforms, just adjust like this, and click on this zoom fit. You can see entire waveforms here, and just click on this waveforms. We can get the marker zoom here. So now we can observe that how the output is varied by varying the A is 0 and B is 0, C is 0. Now the sum is 0 and carry is 0. We can see. Putting the marker on the next test vector, A is 0, A is 1, B is 0, and C is 0. You can see sum is 1, A, B, and carry is 0. So then after you can see the next combination we are getting sum is 1, the carry is 0. Final combination is A is 1, B is 1, the sum is 0, and carry is 1. So here we can observe that the outputs sum and carry, the inputs A, B, C, if the inputs are changed, the output is also abruptly changed without giving any delays. You can see here the output change, the input changes from 0 to 1, and the output is also changes from 0 to 1 at the same time. So this is what concurrent simulation. But there is no delay between this. So if you want to observe that delay is existing between input to the output, so we have to implement this design, and after that implementation, so we need to do the post simulation. Then we can observe or we can get the delay between the output and input. So here we can see without any delay waveforms. So this is also called RTL simulation level. So here we can get the RTL design. That's what logic level or gate level or schematic. Here by elaborating open elaborated design, just click on this schematic, click on. We can see the elaborated design, also called gate level design. It is called RTL level. So this is the RTL diagram after completion of this elaboration. So this schematic shows the gate level design is having two half headers connected with an OR gate and two output buffers. Observe here, the two half headers are connected in such a manner to get the full header operation. So this is about simulation. So we have observed the waveforms as well as the RTL level diagram. So now the next step is synthesis. So to get the netlist of the given written code, so we need to synthesize the design and we can get the architecture hierarchy of this design. So now just go to that synthesis on the left side, click on this run synthesis. So before going to that synthesis, we have to select this full header. Now click on this run synthesis. The synthesis is going on here. You can see run synthesis design. So after completion of this synthesis, it will show this window, run implementation, open synthesis of the design, and you request. So immediately we can go to that run implementation. But so now we are not going to that implementation because we are also going to create constraints. So we are not creating constraints here. So just see that synthesize it is. Just select open synthesization, click OK. So here already elaborate design is open. Now I'm going to go. So here we can see the synthesized design. So here maximize. You can see this is what S0 Y0, S0 Y1, S0 Y2. These are all the slices here. So this is entire JetBoard Zinc 7000 series FPGA. So by zooming this synthesized design, we can observe the CLBC by zoom any area. Now I'm going to zoom. See the internal structure of this. You can see this is one CLB. Here we having number of CLBs. See CLB of 80, 27, 28, 29 like this. Number of rows and columns and countings also there. Here this is one CLB. So CLB having the lookup tables 1, 2, 3, 4. This is one of the slice, and it's having multiplexers to select the lookup tables according to the given logic. So here we can observe flip-flops to store the logics generated by this CLB. Each configurable logic block having different LUTs, a lookup table. See there that the lookup table is six input lookup table. Here you can see this is also six input lookup table and outputs are the two outputs here. So this is about synthesized again, and we have IOBs in this side. Here we are observer input output labs and buffers also there. So these are the IO pins. So now coming to create a constraints file to connect our variables, design variables to the FPGA. We need to create a constraints file. That's what XDC Xilinx design constraints file. To create that constraints file, we are using two methods by writing a TCL script on that constraint file, or otherwise we can use the plan ahead tool. See here, selecting that IO planning, just click on that IO planning. You can observe all ports here, scalar ports. Just expand this scalar ports. You can see what are the inputs and what are the outputs here. Default, it will select some pins here. Just click on this pin A, pin B, pin C. These three are inputs, and C out and S out, carry out and sum out is the output pins. The direction of these pins A, B, C are input here. You can see carry out and sum out. You can see output pins. Here. Now I'm going to assign the FPGA pin names to these variables. So here I am using inputs as dip switches and outputs as LEDs. So previously we have seen that FPGA pins and their names. Once again we will see from this presentation. See the dip switches, switch 0 to switch 7. We have 7 switches. So from these 7 switches, I am using only 3 switches. So these will be so from this switch 0, switch 1 and switch 2, I am using F22, G22 and H20. See input side using F22, yes, F22 is there, and G22, yes, G22 is there, and H20. H20. So here F22 and G22 and H22 I am using from the FPGA. These are called dip switches, dual in pole, and next the bank 35, bank 35, and then the default I'm selecting this LV CMOS voltage. CMOS voltage 1.8. I'm using 1.8 volts. 1.8, 1.8. Here the inputs are selected F22, G22, and H2. So we need to give the pin numbers, directions, default it will take, and select the input output voltages, maybe 1.8 volts or 2.5 volts, or we have 3 volts here. LV CMOS 18 means 1.8 volts. LVC must 25 means 2.5 volts. LVC must 33 is 3.3 volts. Here the board having three different voltages. We can adjust these from 3.3 to 1.8. So I'm selecting this 1.8. So coming to the LEDs, the pins are T22 and T21. LD0 is T22, LD1 is T21. So I'm assigning these two LEDs to the output of the T22 and the T21. So I have assigned T22 for carry output and T21 for sum output. So here also I'm giving 1.8 and 1 LTC mass 1.8 volts here. See, the banks are different. The output pins is LVC mass 1833, bank 33 here. So they're having different banks. So here output selected for LVC mass bank 33. Okay. So now it is added. The pins are connected here. Just save it. So give the constants file name here. Full adder using full operators. You can give any name here. Default it will take HDC file, the same location, local to the project. Click OK. Now you can see constants file, it is added. So very easy to create by using this IO planning. So one more method is, so we need to create a constraints file here by right clicking on this add source and create or generate add a constraint file like this. We can create after creation of this file. Just see double click on this like this. We have to write. So this is what a TCL script set underscore property package pin F22 is connected to the pin A and G22 is connected to pin B. Like this, we have to write the code. This is called a TCL script. So this will connect this FPGA pin to the design variables. So this is about constraints file. So now everything is created. Simulation is over, and now I'm going to implement this design. So this implementation, it will translate the design and mapping the design. After that, it will create a bitstream file, place and route it. After that, we can generate the bitstream file. So now I'm going to implement this design. While going to implement this design, so we also update that the synthesis. So just go to that implementation, run implementation. So before going to that implementation, we can see here implementation settings. So here you can observe that optimization of the design, optimal design, power optimization, place and route, that's what place designing, post placement. These are all the optimization designs. So we can select these designs, optimization. Here default it is selected. So we can optimize by power by clicking on this power optimization design. So now I'm not selecting this power optimization. Before power operation, how much we get? Then after we will check it. Just click OK and click on this run implementation as well. You can see the synthesize. After synthesis, it will shows implementation and after. So here, after completion of this implementation, we can see open implemented design. or next go to the generate decision. So before going to that bit stream generation, we will go open implementation design. You can observe the implementation place and route and timing constraints also. I open this. Okay. Now you can since the design is already open, now it is going to close. So here we can see that implemented design. So we have network planning. So these are the things. So you can see the schematic of the design up in the schematic also. You can see the synthesized schematic design. Here A, B, C are the inputs here and outputs carry out and support. Here we are using LUT, so 3 input LUT. Here is 3 input LUT. Total 6 input LUT here using. So having the two outputs, it may be utilized. You can see the report of utilization and power and timing. See one by one. So that timing and type report underscore utilization. Otherwise, click this report utilization. Click OK. So you can see here full header name is having utilized one LUT and five IO, three inputs and two outputs. You can see on the summary of this utilization. See this. The available slices are 53,200. I am using only one slice and 200 IOPs are there. From that I am using only 5 IOPs. So utilization in terms of percentage, you can see 1% is slices and 3% of is IOPs. This is what utilization. See, you can IOPs 1, 2, 3, 4, 5, and 1 LUT. So by clicking on this design summary, you can see the project summary also. See the utilization and by giving table, the resource LUTs, how many are utilized, IOBs are how many are utilized. This is what graph, power consumption by this device also you can see there. The dynamic power 0.927 watt, 87% here, and the signals consumption 0.044 watts, and logic there 0.007 watts, and IOB is 0.87. Maximum power consumption by this IOB. Here, the static power is zero point 0.1. The total power of this is 87 plus 13% is 0.927 plus 0.13. Now, we can go to the report timing is. going to observe the timing summary. Report underscore time. You can see report underscore timing summary. Just enter here. You can see timing details. Here you can see the timing summary. So from A to the from output 5.328 total delay, and the logic delay is 3.78. So here the logic delay is 3.78 and net delay is 1.6. Net delay means the routing delay between A to the sum, and logic delay is switching the gate delay. Logic delay is gate delay. So in that gate we have MOSFETs. Those are switches from 0 to 1 or 1 to 0. Those will connect the input to the output. So that is a logic delay, also called gate delay. So summation of these two, they are cutting a total delay. Yeah. And path for A to carry out is also having total delay. You can see in the schematic the path for by clicking on this. See here A to S out. So this is the path. This path has a delay of 5.328. Next, so clicking on this A to carry out. This path has delay of 5.31. Next, you can see T2 some order. Just click on this. This path has total delay 2.016. This path has the total delay, so 2.0. So we can observe the total delay like this. This is called timing summary. So now we are going to implement a device. See, to maximize the device, we can see our design by clicking these IO ports. Here you can see this connection. The routing of this. Here, this is what A. We are clicking on this. This is B. Only routed nets resource. You can select it. All nets are only routed nets here. C out. C out. S out. A. You can see that the routing of all these. This A is connected like this. See the connections of A. These are routing. This is your logic. This LUT is used. 1, 2, 3, 4, 5, 6. A single LUT is applied. The logic is implemented by this LUT only. See here, the green line shows the routing of this logic. So this routing is connected to the high volts. And select B also. You can observe the routing. So everything is connected from this LUT only. Single LUT. You can observe everything here. This is the routing. It's one part. You can see this. Everything is utilized from this. So the logic is developed by using this LUT. So this is about routing and placement. The placement already is fixed. So now our design is converted into a product on that FPGA. This is something. So now, after completion of this implementation, I'm going to simulate the design once again. That is called post simulation. So go to that simulation block. Just click on this run simulation and select this run post implementation timing simulation. Now we can get the delay after this simulation. Simulation is so now we can see post simulation, behavioral simulation. Both simulations are available here. So just zoom it. This is post simulation here. Now you can see simulation having a delay. It offers 8.437 delay between input to the output. That is called the propagation delay. See here. So input is 0, output is 0. Input changes from something, but it, see the output is available after 8 months. So this is what the propagation delay, initial delay. Also. Previous diagram before implementation, the pre-implementation, I see here, no delay offers. So the two inputs are there, the output is available here. If there is no delay in that behavioral simulation, but you can see the delay after post simulation. You can observe that after 8 nanoseconds, the output is available. This is called a post simulation. This is the beauty of this simulator. So now I'm going to final step. That is what bitstream generation. So to generate a bit file, so going to that bitstream generation, just click on this generate bitstream. So bitstream is generating right the bitstream here. So after completion of generate the bitstream, so go to this open hardware manager, click open. So this is what the final step. So it will open that hardware manager. If your FPGA is connected to this device, this system, it will open the target. It will connect automatically, or you can select the target. After this uh, connection, we can implement that in FPGA. So this is the process of implementing a design into the FPGA. Here, no device is selected because FPGA is not available here. So So the final step is just select the device and implement on that FPGA. This is the final step. So with this step, I will conclude my presentation here. So how to simulate and how to synthesize and how to implement on FPGA, we have discussed everything, and how to uh, find out that power consumption, and how to find out the timing between input to the output, that is what the propagation delay using this tool. So we have discussed everything, pre-synthesis, pre-simulation as well as post-simulation also discussed here. Thank you. Thank you for your patience.